Hello, I'm Stephen Waterman, and this is Prototype It with SAT. At this point, you probably have two questions. Who are you, and what is a SAT? Well, we'll start with the easy one. Who am I? Well, I'm a software developer at Scott Logic, and I have proof in the form of cheesy promo materials. Okay, wait for it.
Service sector and actually
there, no, wait, there. There I am. Currently, I'm just living that furlough life, staving off boredom by streaming on Twitch 5 days a week, live. So, what's a SAT? SAT, which is short for the Boolean Satisfiability problem, is the problem of determining if there exists an interpretation that satisfies a given Boolean formula. In other words, SAT is confusing, but actually it's simple. Rather than trying to explain it in words, let's just look at a visualization. SAT is a simple problem. Given these 5 Boolean variables, how can we set them to true or false so that all of these clauses are satisfied, where each clause is some of our variables ORed together, or their inverses. In this case, I could set A, C, and D, and that would satisfy all of them. I could also just set B, C, and D, that works too. The thing is, in order to find those solutions, I basically just had to brute force it. It's really easy to work forwards and say, if I've ticked these variables, which clauses are satisfied, therefore is the whole thing satisfied? But it's really hard to work backwards and say, what do I need to set these variables to in order to get that all true light to come on? And that's what SAT Solver does, is it works backwards. So that explains what SAT is, but it leaves one question. Why? Why should I care? I've never needed to do that. None of my programs have ever needed to do that. But the thing is, they probably actually have. SAT is NP complete, and that means two things. One, it's really hard to find an answer, and two, it's really easy to check an answer. Of all the problems like that, SAT is the hardest. And that means, really, that a program which can solve SAT can be used to solve anything that is easier than SAT. And since most things are easier than SAT, that means it's really just a thing solver. In a minute, we're going to live code a meal planning algorithm. I'll be using GNU Linear Programming Kit, a C library with TypeScript bindings. It isn't actually a SAT solver, it's a linear programming solver, which is like a more general kind of SAT. Let's just have a quick look at how linear programming works. In SAT, all of our variables were Boolean, either true or false. However, when it comes to linear programming, our variables can be any number. We do constrain them further, so for example A here is any integer between 0 and 10, and D is any number between 0 and 2. However, it's a much wider range of options for each variable. Where in SAT we had clauses, in linear programming we have constraints. A constraint is made up of a coefficient for each variable and some bounds. For example, constraint 1 says that 3a minus d plus 4e has to be between 35 and 45. When all 4 of our constraints are satisfied, although you're allowed any number, then the solution is valid. The other thing that linear programming gives us is this objective row. The objective row comes into play once the solver has found a valid solution, and it tells us which of the valid solutions is the best. The solution with the highest objective value is the optimum solution, and that's the one that the solver will try and find. Like with SAT, it's really easy to work forwards, so looking at our variable values, looking at the constraints, seeing whether they're valid, and calculating the objective value. But it's really hard to work backwards. It would be essentially impossible for me to find a solution, never mind an optimal one. But GLPK is really good at it. Let's see that in action. So, to start off with, all of the variables are 0. Even B, where it has to be between 4 and 20, the solver will start with all variables at 0. Then, as we iterate through, it will slowly start trying to find a valid solution, getting closer each time. Eventually, it will find a solution, and we can see that all of the constraints will be satisfied. Not quite. There we go. So now it's satisfied all 4 of those constraints. At this point, it will start moving in the direction of increasing objective. So it's currently 62.53, but the next iteration it goes up to 63. Then it goes up to 66, and then finally up to 66.4. At that point, it's found the maximum value for the objective. However, you'll see that the b variable is currently 9.8, but b is required to be an integer. So we found the optimal solution, but not the optimal integer solution. It will look at all of the integer solutions near the optimal solution that it found, and it will pick the one with the highest objective. In this case, it will set b to 10, and therefore c has to go to -8 to keep all of our constraints satisfied, giving us an objective value of 65, which is the optimal. So, now let's move on and see how we can model the problem of meal planning as a linear programming problem. So, now we're going to have a look at how to do some meal planning. We're going to start off with just a kind of skeleton of a project here, which creates a new linear programming problem and then solves it. It currently doesn't do anything. It doesn't have any variables or any constraints, and that's what we're going to be doing. The first thing that we need to do is add some variables which tell us whether or not we ate a given recipe on a given day for a given meal. So, did we eat cereal for Monday breakfast? So that's going to be for each combination of days, meals, and recipes. And we want to say for each day, meal, and recipe. And we're going to do something with that. Let's just import all of those from our inputs and our data files. So inputs is where the user tells us what their constraints are, how many calories they want to eat. And we'll see more of that later. But for now, for each combination of day, meal, and recipe, we want to create a new variable. We're going to say 8 recipe.name for day, meal. So did we eat that recipe on that day for that meal? So now we need to give it some metadata, which just helps us distinguish between our variables once we've created them. And we're just going to set the day, the meal, and the recipe. Then we need to give it the bounds. So the minimum value is 0, the maximum value is 1, and allow decimal false. And what that does is essentially it makes it into a Boolean. 0 or 1, nothing in between. Finally, we need to give it the objective coefficient, so that number along the bottom, the reward for setting this to true, is going to be the rating of the recipe. So how much does the person like that rating? Now, if we run this, we should see a meal plan, and we do. It's quite a packed meal plan. It has every single recipe for every single slot, but that makes sense. All we've done is we've asked the solver, would you like to have cereal for Monday breakfast? And if they say yes, then the objective function increases. And then we say, would you like avocado toast for Monday breakfast? And repeat. So a really obvious first thing to fix would be not allowing more than one thing per meal. So we're going to say that for each combination of day and meal, so we take in day, meal, and what we're going to do is say new constraint, number of recipes eaten for Monday breakfast. So day, meal. That needs to be at least 1 and at most 1, so that we have something for every single meal. Then we need to say which of our variables contribute to this constraint. So we're going to do that based on the metadata that we set before. And basically we're going to say if the day is correct and the meal is correct in that metadata, then we're going to return 1. So the coefficient of our variables is 1 if they're for that day and that meal, otherwise it's 0. Now if we run that again, we should see that there is only one thing per meal. And we do. Chocolate cake. Oh no, I think those are actually chocolate brownies. Chocolate brownies for every meal of every day, which, while it sounds delicious, is probably not what you were imagining when you thought of this meal plan. And the problem is that not every recipe is appropriate for every meal. We actually have this in our data, so we know that for a given meal and a given recipe, we can look in that recipe.allowed meals, and that tells us which meals it's allowed to be in. So we're going to reduce the number of variables we have by only having variables where the meal is correct for that recipe. So we don't have chocolate brownies for breakfast. Now what we see is that we're having appropriate foods for every meal, and we're only having one. So we're having avocado toast for breakfast and lunch, spiced carrot soup, I think that is, fish and chips, and then chocolate brownies. Fantastic. But the next thing that I notice that's a problem is that this avocado toast is happening twice per day. Nobody wants avocado toast twice a day. I mean, I realise that it's a whole trend and everything, but... So, for each combination of day and recipe, we want to limit the number of times that you're allowed to have it. So, we're going to say a new constraint, number of recipe.name on day. Number of avocado toast on Monday. And that needs to be between 0 and 1. You can't have 2, or 3, or any other number. So, which of our variables matter for this? Well, it's the ones where the day is correct and the recipe is correct. And if both of those are correct, the coefficient will be 1. They will contribute 1 to this because we're just counting. So, if we run that again, what do we see now? Well, we should see that we're not having avocado toast twice a day. Instead, we're having club sandwiches for lunch. But I do see that all of these days are the exact same, which makes sense. There's no reason for them to be different. But in real life, things change between days. I have a different amount of time available to me each day for cooking. So for each day, we're going to create a new constraint. And it's going to be time spent on day. So how long did we spend cooking? The minimum is going to be 0, and the maximum is going to be user provided for each day. So we're going to say that the max is the max time on that day. And what that gives us is, over here, we say that on Monday we have 60 minutes, up to on Sunday we have 3 hours. The last bit to do is the coefficients. So we're going to say that a variable matters if its day is correct, and if, in fact, that's the only thing that matters. So if the day is correct, then if it's 1, we want to add the amount of time taken by that recipe. So if the variable cereal for Monday breakfast is true, then we want to add the amount of time it takes to make cereal to the total time spent on Monday. And if that's too high, it will be invalid. So if we run that again, we should see that things are different between each day, because, although we don't, the reason that is because actually 60 minutes on Monday isn't enough time to cook 5 meals, because we've got breakfast, lunch, starter, dinner, and dessert. That's not enough. That's too much food to cook in 60 minutes. But nobody eats starter and dessert every day. Nobody eats breakfast on weekends. So actually, some of those meals are optional. Where we said that the minimum number of recipes eaten on that day meal is 1, really it should be 1 or 0, depending on some factor. We're going to leave that up to the user. So we're going to say that we're going to have this meals required list, which is basically just a big list of, is this meal on this day required, true or false? And if the meal is required on that day for that meal, then the minimum is going to be 1, but otherwise it's going to be 0. Now, if we run our meal planner again, we should see that actually, yeah, we're going to reduce the amount of things that we eat each day. So on Monday, Tuesday, and Wednesday, we're not going to eat anything for our starter. Then on the days where we have more time, like Sunday, we are going to eat every meal. And again, now you see that actually we're eating different things each day. So Wednesday compared to Thursday, we're eating different things. However, this is quite a cheeky meal plan, really. I think most people are using meal plans to reduce the amount that they're eating and take control of their diet. So on Sunday, when we're eating Victoria sponge and fish and chips and a club sandwich and avocado toast and spiced carrot soup, I think that is, that's quite a lot of food. We should really be taking into account the number of calories that we're eating. So let's also constrain the amount of calories that we have each day. So for each day, we're going to say new constraint, calories on day. The minimum number of calories is going to be the calories min, inputted by the user, and the max is going to be the calories max, again inputted by the user. Currently we're on 1700 and 2200 calories. So, and then which of our variables matter? Well, it's the ones where the day is correct. So if meta.day is day, then we're going to return the number of calories in that recipe. And that's per portion. So now if we run this again, then we can see that we're eating 1,700 calories a day by having much kind of heartier foods. And then on some days we eat up to 2,200. However, one thing that I notice is that actually a lot of these foods are quite low in calories. And that's because they're using the manufacturer recommended portions, which is often like one brownie or one pie. Nobody's just eating one brownie or one pie. So actually, we should be taking into account the number of portions that you're eating. So up at the top, where we define our variables, we're going to define a new variable, a second one. This one is just going to be a Boolean of did we eat that? And then we're also going to have a new one of how many portions did we eat? The new variable, portions of recipe.name for Monday breakfast. We still need the same metadata, although actually now we need some more metadata. Not just day, meal, and recipe, we also need what type of variable it is, because we have two types. There's the portions variables, and there are the eaten variables. And that will just help us distinguish what kind of variable we want to constrain. Then we need the bounds. So the minimum number of portions is going to be the recipe portions min. So for each recipe, the user will specify how many portions they can eat, minimum and maximum. So you can say like, yeah, I can eat 2 to 3 brownies, or half a portion to 1.5 portions of risotto. And that actually is where this comes in. So not all recipes you can have a decimal amount. You can't eat like 0.33 of a pie, at least a small one, big one maybe. But we're going to let the user say whether or not that makes sense. So recipe.portions.allow decimal. So there are our bounds for that. And we're not going to set an objective value like we did with that, because actually the rating stays the same no matter how much you eat. Maybe there would be a little bit of a like increased rating if you had a bigger portion, but that's outside of what we're going to worry about. So there's one problem with this, which is this min. Currently that's saying that for every meal, on every day, for every recipe, we must eat at least the minimum number of portions. But that doesn't really make sense. Actually, most of the time you eat 0 portions. This is what's known as a semi-continuous variable, which is where it has a minimum and a maximum, but it's also allowed to be 0. The way that we handle that is that we have a Boolean which tells us whether or not we have any. So this is basically like eaten works as saying portions non-zero. And then we add a couple of constraints which can like bind these two together. So first of all, we say a new constraint which says, so if eaten greater than 0, portions must be 1. Oh, sorry, wrong way around. If eaten is 1, then portions greater than 0. What we're going to do here is we're going to say that the minimum value is 0, and then we're going to define our two components. So we're going to add to this constraint whenever we have a number of portions. So we're going to add the number of portions that we're having, and then we're going to subtract the minimum number of portions whenever eaten is true. So what this means is that portions will push this number up, and eaten will pull it down. We need to say that it's above 0, so we can't have eaten, which will pull it down, unless we also have portions, which will push it up. We can then do the opposite and say if portions greater than 0, then eaten is 1. So again, the bounds, the minimum is 0, and our components, so we're going to subtract the number of portions, so portions will pull this number down, and then eaten will push the number up by the maximum number of portions. So if you have any portions, it'll pull it down, and then you're required to have eaten to push it back above 0. That's enough to combine these two together and get our semi-continuous variable. The only other thing left to do is to look at these where we have our constraint definitions, because now we have more variables than we had before. There are two kinds, and we need to refine these selectors to say that we only care about one type of variable. So the number of recipes eaten is just a Boolean. We just want to count true or false. Same for the number of recipe on that day, so we're just going to constrain it based on eaten, not based on anything, not based on the portions. When it comes to the time spent, for our purposes, we're going to say that it doesn't matter how many portions you have, it takes the same amount of time. But for the number of calories, that does matter. So for the number of calories, we want to say that it's based on the number of portions. And because this is a coefficient, this means that actually this is the calories per portion, and we're going to multiply by the number of portions that you ate. So let's run that again. And now we can see that we're not just having one portion of each. We're having 2 or 3 portions of things to pump up those calorie numbers. And this is where we're going to end, really. All in all, that took around 15 minutes to code. Admittedly, that was a practiced run-through, but I could do something similar from scratch in around an hour. While it was a lot of code, about 100 lines, it was quite easily digestible and intuitive. Each section did exactly one thing, and could be removed or changed without having a knock-on effect. That's one of the best bits about constraint-based solvers like this. You can start with something really simple and then iteratively build up over time. At the end, you have a fully working solution, but your code is still kind of modular. It's clean and it's maintainable. We could have very easily kept going, iterating more and building in more features. For example, we could have set the max time on a per meal basis, or we could have considered the total cost of a meal plan. That second one is especially interesting, as it would mean adding a second component to our objective function. We could then let the user set a weight for each component, allowing them to generate cheap meal plans, tasty meal plans, or to prioritise somewhere in between. The final version of our meal planner took around 60 milliseconds to run. That's pretty fast, especially when you consider that there's on the order of 10 to the power of 30 possible meal plans, and it found the one option that was optimal. If you think back to that linear programming visualization that we did, try and imagine it with 350 columns and 700 and something rows. Kind of ridiculous. As I mentioned, GLPK is guaranteed to find the optimal solution. However, if we don't care about which option is best, we can just set a time limit and the solver will output its best solution at that point. That'll be necessary if we started to add more variables, because it takes exponentially longer to find the optimal solution as the problem grows. There's just no getting away from that exponential growth. While GLPK and SAT are fast, they're certainly not as fast as a handmade algorithm that just does one thing. Taking the example of Sudoku, SAT-based solvers are around 50 times slower or 2% as fast when compared to the state-of-the-art handmade single-purpose solvers. That gap narrows to around 10 times slower or 10% as we focus on the hardest Sudoku. That's because there are less corners that the more advanced algorithms can cut, and there are less tricks that they can use based on our contextual knowledge of Sudoku. Interestingly, most real-life problems are actually much harder than Sudoku. It's got a much bigger solution space. As the problems become more general and the complexity increases, SAT solvers or constraint-based solvers get closer and closer in performance to the handmade single-purpose solvers. It's hardly surprising that JCZ solve is so much faster than a SAT-based solver. It's the product of years of academic research into Sudoku solvers. Plus, it was a community effort built up over many years. It takes full advantage of our contextual knowledge about Sudoku and has been ruthlessly optimized, even to the point of being designed to work on a specific CPU to fit inside cache lines and all of that. If you asked me to try and make my own version of JCZ solve, it would probably be at least 1,000 times slower, and I mean that like legitimately 1,000 times slower. And it would take me days. To get anywhere near their speeds, I would need a team of researchers and months, if not years. If you asked me to make my own version of a SAT-based solver, though, it would take me an hour, and it would be probably half the speed of the best SAT-based solvers. So much quicker for me to get close to the state-of-the-art performance. SAT solvers are modern miracles. They give you access to 30 years of academic research, and in an amazing turn of events, are freely available, easy to understand, and actually work, which is a rare find in academia. So who should consider using SAT solvers? Actually, no. Who shouldn't consider using SAT solvers? So you shouldn't use a SAT solver if your problem requires maximum speed, you have months or years to work on it, and you have a team of researchers sitting around waiting to do something, i.e. if you are Google. If you aren't Google, so if developer time is precious and could be spent on better things, if you don't have many users, or if you need it to be done quickly, even if it's a little bit slower, then SAT is probably perfect for you. In other words, if you're a startup or you're prototyping something, SAT would be great. It all boils down to this. Using a SAT solver, rather than handwriting a custom algorithm, trades high upfront costs for high variable costs. In other words, you save loads of money upfront on developer salaries and free them up to work on something else. However, you end up with an algorithm that's only half as fast. But that's where those variable costs come in. If you have an algorithm that's half as fast, you could just run it on twice as many compute nodes. So if it would have taken 4 compute nodes with a handmade algorithm, run it on 8. Sure, it'll cost more, but then that cost comes further down the line, and more importantly, that cost scales with the number of users. Because you need less compute if you have fewer users. So for a startup, when you have few users, it's ideal. That cost is actually fairly negligible. If your startup or your prototype is a success, it will outgrow this constraint-based solution. It will become too expensive to keep paying those higher compute costs, and you will have to write that custom algorithm anyway. However, at that point, you've already validated that the idea is actually worth working on, and you have enough users to support that high fixed cost of having to spend the time to write it. The reality is that most startups don't actually make it to that point, and any startup that starts its life with a huge R&D cost to make this custom algorithm is almost guaranteed to fail. Until you know that your product is actually useful and in demand, just prototype it with SAT. Thank you all so much for watching. I hope you've enjoyed it. If you want more from me, I stream on Twitch every weekday, twitch.tv/Stephen Waterman. I'm on GitHub and write blogs and other things as well, but come talk to me in person, or rather not because coronavirus, but talk to me in the Q&A. I'm happy to answer any questions. If you want further reading, there's some links in the description, including one of my blog posts about using SAT solvers to do sprint planning, as well as the incredible SAT solvers Fast, Neat and Underused, which inspired this talk. Enjoy your lunch and enjoy the rest of the conference, and I'll see you at the Q&A.